Okay, so I will speak about the equation of motion of a slender rod that is rotating about a fixed axis. So let's say we have a pin. It's a pin connection that is attached, let's say, to a ceiling. And we have a slender rod that is pin connected at the point O. Okay, and we release this slender rod and it's rotates. So let's use another, so it's rotating about the point O. Let's make a circle. So let's say at 45 degrees, it will be there, and 90 degrees, it will be there. Okay, so the first question that we will try to answer is, let me move this, oops, it's what is the alpha at any angle? Okay, so that's alpha. So I will use the slender rod at the, let's say 45 degrees positions, kind of 35 degrees position. It's not 45 degrees, it's kind of, it's theta. Okay, so we will use the position of the slender rod of theta. So the first thing that we need to do is free body diagrams and kinetic diagrams. Okay, I will make them separately. Let's move this one a little bit above. Here we go. Okay, so it's pin connected there. Let me just write the pin connection. For the kinetic, what do we have? We have an angular acceleration alpha and an angular velocity alpha, omega. Okay. At the point G, I should not write this one there. I need some space in the middle. That's alpha, and that's omega. Okay. Now we are on the body, so we need to use the acceleration at G. So let's draw the point G. It's in the middle there. That's my point G. Okay. And in rotations, our favorite axes are the normal and tangential axes and normal and tangential acceleration. So it's rotated about the point O. Let me write O. So my acceleration, that's the A of the gravity center G, tangential, and it's going down, left and down. Okay, that's the path of my point G. And the normal acceleration is always toward the center. So that's A of the point G, normal acceleration. Okay, so that's for the, if you want to be a little bit more precise, we can add M in front. Oh, I like this one better. We can add the mass in front. I write it in blue because we know the mass. It's given. It's one information that's given, and the mass there. Because in our equation of motion, we have some of the forces on N. So let me write them there. We will have some of the forces on N equal M AG N, and some of the forces on T is equal to M AG T. That's why I like to write MA for on the kinetic diagrams. Now on the free body diagram. So this one is the kinetic diagram. And this one is the free body diagram. Okay, so what do we have? At G, we have the weight going down. And let's say it's mg because I use international units. Okay. And it's also mg if it's slug and the weight is in pound, but what is given is the weight. And in this case, we need to find the mass. Anyway, we have, it's a pin connection. So pin connection means two unknown, O, Y, and O, X. Okay, I write it OX and OY. We can choose if we want to write ON and OT, but I prefer to find them in terms of X and Y. Okay, so we can use, we will write the equation on T and on N, or on X And on y, okay, we can choose, but we need to be consistent when we write the equation of motion. If we used to use x and y for the force, we need to resolve the axis at the acceleration AGT on x and y and AGN on x and y. If we decided to use n and t for the acceleration, we can use n and t for the pin reaction at O, and we need to resolve OY and OX on the axis n and t. Okay? Just be consistent in your equation at the end. What we need some dimensions. So you forget to say that the length of the road is L. So it means that this dimensions is L divided by 2, or this one is L. And we need one last dimension. That's the geometry for the angle theta. The position of the angle right now is theta. Okay. Which equation is the most convenient to use for the moment when it's a rotation about an axis? That's the moment about the center of rotation. So sum of the moment about the point O is equal to I-O alpha. And remember, we can use I-O alpha only because that's the center of rotation. We can otherwise use sum of the moment about G equal I-G alpha. Okay, but in this case, because we are in rotation only, we can use, and we prefer to use, sum of the moment about O equal IO alpha. Thanks to these equations, we will be able to solve for alpha. Okay, so let's do the sum of the moment about O. Okay, so that's our free body diagrams, that's our kinetic diagram, and that's our three equations. So 1, 2, and 3. Okay, let me check. Okay, so sum of the moment about O is equal to IO alpha. We like these equations because the pin reaction at O are not including inside these equations because they are at O and we take the moment about O. Okay, and any force that is going through the point O doesn't create any moment at this point, about this point. So at O, the only force that creates a moment is the weight. Okay, and it's going in these directions. So minus the weight time this dimension there, that is L divided by 2 times cosine theta. That's the adjacent side, that's this one. And we take the perpendicular distance to the vector W. That's the only force that creates a moment about O. And on the right, it's equal to IO alpha. How much is IO if you look at your formula sheet with the mass moment of inertia for a slender rod? IO is equal to 1/3 of ml square, or you can use IG equal 1/12 of ml square. Let's use right away 1/3 of ml square, it's given. So we have minus WL divided by 2 cosine theta, it's equal to, when do I include the alpha? Let's do it there. So 1/3 of ml square, and alpha, okay, I should write it there already, okay? Minus, why? Because alpha, my accelerations, is on the negative directions. So minus 1/3 of ml square alpha if I want to be consistent, okay? So minus minus on both sides, plus plus. W is mg, so I have mg, L divided by 2 cosine theta, it's equal to 1/3 of ml square times alpha. Okay, m and m on both sides, and L square, so we just have L left. So on the left, we have g cosine theta divided by 2, it's equal to L divided by 3 alpha. So finally, we have alpha that is equal to 3 divided by 2, 3 alpha time g cosine theta divided by L. So at any time, we are able to find the angular acceleration alpha anytime. I will say for any theta, we don't know the time, okay? We don't have any information for that. But at any theta, for any positions, we can find the angular acceleration, okay? And when is it max? So we have our little triangles. That's my cosine on my axis x. So cosine is maximum with theta is minimum. So when cosine 0 is equal to 1, cosine of 90 will be equal to 0. That means that alpha for theta equals 0 degrees is max, and it's equal to 3/3 of g divided by L, and theta at 90 degrees, it's equal to 0. So the angular accelerations here, oops. Okay, so my alpha here, it's equal to 3 divided by 2 g divided by L, and my alpha here, it's equal to 0. And if you want to find it at theta, it will be equal to 3 divided by 2 g cosine theta divided by L. So we are able to find the angular acceleration for any position. So that's it for the angular acceleration. We will see some other information like the pin connections in the next video. Thank you.